All right, folks. I know some of you guys have been struggling to sort of figure out exactly how to use your Z tables and how to go back and forth between Z statistics and percentiles. So I want to show you a quick example of all of that. The problems that I'm going to go over are part of the larger practice problem set that I've included for this unit of the course. You do not have to do any of these problems, of course. That's why they're just practice problems in case you feel you need a little bit of extra help. And so I grabbed a few right out of there so that when you work on those problems, you can kind of see if you're on the same page, right? Okay, so we need a calculator, we need our Z table, need something to write with, obviously, and then the problems themselves. So in this first problem, it says, please find the z-score that corresponds to each of these percentiles. So we're told the 27th percentile, right? Which means 27% of the population falls at or below that score, right? So that's below 50th, and we know the center of this distribution is 50th because there's half above and half below. So the 27th is going to be somewhere over here, right? So I'm just going to sort of arbitrarily draw a line, doesn't matter if I'm actually right about this, and say that 27% is this over here, right? 27% between the score and below, right? So our Z table does list this in column C. I tend to use column B more frequently. So column B is the area between the mean and Z, which means this section here between the mean, the center of the distribution, and the Z score right here. So we need to look up the percentage that's associated with 50 minus this, right, or 23%. So we're going to look in this B column for the score that most closely meets 23%. And what we can see is there's a score here of 0.2291 and 0.2324. Now, because we're trying to estimate the z-score based on that percentile, we want to be a little bit conservative here, if you will. So instead of estimating this one lower, which would inflate the percentile, we want to estimate this slightly higher. So when given the choice then between 0.2291 and 0.2324, we're going to go then with a 0.2324, the slightly higher value here, which then will slightly underestimate our percentile. That value then, as we see in the table, is a 0.62. 0.62. Remember, it's below 0. We're on this half of the distribution, so it's a negative 0.62. So negative 0.62. Okay, next problem. This one asks for the 96th percentile, right? 96th percentile, which means it's going to be way over here because 96% of the scores fall at or below that. So again, I'm just going to arbitrarily draw one over here and say this is the 96th percentile, which means 96% is this entire section over here. Well, we know that this is the 50 mark, which means this half of the distribution is 50%, which means this 96 is made up of this 50 and this 46. That 46 is the percentage between the mean and the z-score, and so we look to our table now for the score that corresponds to 46. You can see it's not quite on this page. We've got to switch to our next page, and we can see then that the value we should come up with here is, there we go, 0.4599, or 4% in the tail, 46%, and so our z statistic is 1.75. All right, so let's look at the third problem here. In this case, we have a third percentile. So again, way below the mean, way over here, only 3% at or below that score, which means with 50% over here, that remains 47% of the distribution. So 47 between the mean and z. And if we look this up, we can find that value here to be 1.89, but remember it's negative, right? It's on this side, so that is a negative 1.89. Okay, and that's how you go from percentiles to z-scores. Always, if you have to, draw this so that you can keep in mind whether or not you're on the left or the right, so you know if your z-scores should be negative or positive. Draw your z statistics, your rough approximation of where they might be, so that you can really think about what the value in the table is giving you, because it gives you in column B the percent between the mean and the z. Between the mean and the z. So you have to think that if it's a percentile for a negative z-score, well, then you have to do 50 minus that to get the percentile below the z. Or you can look at column C in your table, and that works as well. Okay, let's look at the next type of problem. In this case, we're just going in the opposite direction. So we're going to start with the z-score, and then we're going to go to the percentile. So this z-score is negative 1.65. So I can be a little more accurate about where I draw this, since I can see the values of z down there. And all I have to do now, this is easy, is go straight to the table and find the value of 1.65. This tells us there's 45% between the mean and z, right? So that's 0.45 over here. But percentile is how many scores fall at or below that score, right? This little shaded in section. So that would be 50 minus 45, and we would say that this person was then in the 5th percentile, right? 50 minus 45 is 5. Okay, next one. Next one says 2.23, right? So I can draw that in over here. 2.23. Remember, percentile is how many scores fall at or below. We know there's 50% on this side, so we're really just trying to figure out what this percentage is here. So let's look at our table for 2.23. All right, that table's getting caught on my other pieces of paper here. 2.23 is all the way up here. It says 48.71 between the mean and z, which means this section over here is 0.4871. Remember, that's a 0.5, which means this would be the 98.7th percentile, which you'd round up then to the 99th percentile. All right, so one more of these just to make sure you really get this. Another negative one. So negative 0.83. Negative 0.83. Percentile is all this section. Right, so let's look up the value of 0.83. First page now. Flip over. 0.83 tells us between the mean and z is 29.67. So that's basically 30%. So between the mean and z, this section here is 30%. So then what's below the mean and z? Well, that would just be 50 minus the 30%, which would be 20. And so we would say they are in the 20th percentile. Okay, so that's how you do these types of problems. Now, the next type of problems in that practice set, which is, again, the reason I'm giving you these, are they're representative of what you'll see on the exam, asks you, for each of the following hypothetical experiments, you should identify A, the hypothesis, whether it's directional or non-directional, whether the design warrants a z-test or a particular type of t-test, and then determine the critical value for 3 different possible alpha levels, 0.01, 0.05, and 0.1. So 3 different p-values. Okay, so let's see how we would do this. What's our first example? In national use, a vocabulary test is known to have a mean score of 68 and a standard deviation of 13. So before we go any farther, national use, so we know that this is a population average. The population average is 68. Standard deviation of that population is 13. A class of 19 students, n equals 19, takes the test and has a mean, a sample score of 65. X bar equals 65. Now, before we go to the next type of test, let's do our hypothesis. We don't know whether or not this person is predicting them to be higher or lower, because all we know in this example is that a class took a test, they have a mean of 65, and the question is, are they different? Not are they higher than the average, or not are they lower than the average. So really our research hypothesis has to be non-directional. It has to say something like the students are different, right? The sample of students is different from the national average on the vocabulary test. Okay, something like that, right? The research hypothesis saying there will be a difference between the average of the student's performance on the test and the average that we know to be the national average. That's not predicting that one is higher or one is lower. It's saying that there will be some difference in some direction, right? Which means it's a non-directional hypothesis. This just means that our p-value of 5%, let's say for that particular case, would be split into both tails. So 2.5% in each tail. Now, we also know population mean and population standard deviation. That means we're sort of in that ideal world where we know a lot about the population and we don't have to assume anything based on sample data, and instead we can perform a z-test, right? Because remember, the z-test says z is equal to sample mean minus the mean of the comparison distribution, the distribution of means, divided by standard error, right? We know these things because we can get standard error from standard deviation using sample size. Okay, so we got our test. Now find the critical value for each of the following p-values. Okay, so it's a z-test, so we are using our z table, of course. It is a non-directional test, which means that when our p-value is 0.01 or 1%, that means that 1% is split into each side of this distribution. So it's way down here, right? Super low, where we would have 0.005, right? Or half a percent. And again, it's in both directions, right? Because it's a non-directional test, so we'll have a plus minus value here. And so we leave 5% in each tail. So now we need to find a value that corresponds to when there is that small of an amount in that tail, right? What's the z-score going to be? That means, for reference, that 0.4950 would be in the center of the distribution, right, on both sides. So that's what we're going to look for, a value close to 0.4950. And we should find 2.58, right? So for a 0.01 value, we would have a plus minus z-statistic cutoff value of 2.58, which means our z-statistic from our problem that we would get up here, which we're not calculating, would have to go higher than 2.58 or lower than negative 2.58, right? Okay, how about the next example then? The next one says a p-value of 0.05. So that's our traditional one. That's 5% total, which means 2.5% in each tail, right? And so in this case, we would want to sort of shade a slightly larger section here. Right, it goes a little bit farther out because it leaves 0.025, 0.025 in each part of the tail, right? In this case, that would leave then 47.5 in the middle of the distribution. So we go and we find the value that corresponds to 0.4750, find that one over here, and that is our cutoff of plus minus 1.96. Okay, last one, critical value now for a p-value of 0.10. 0.10 is going to be even less conservative, right? A little bit more liberal, leaving a full 5% in each tail, right? So leaving 0.05 in that tail and leaving 0.05 in that tail, which means that, of course, that you would have 0.45 in the middle of the distribution. So we head back over here, we find the value that corresponds to 0.405, and we see 0.405 for 165, and 0.4495 for 164. In this case, we're trying to find a cutoff value that determines statistical significance. So we don't want to use the lower one because that just makes it easier. We want to make sure that we are truly finding that our effect is statistically significant, and we can be more confident of that if we use the higher z-score cutoff. Okay, so we're going to use the 1.65. All right, does that make sense? Okay, well, I can't hear you because this is a video, so hopefully it did make sense. All right, now the bigger problem. This one says, for each of the following hypothetical research studies, you will need to conduct the appropriate hypothesis test. Doing so will require you to A, identify the design, B, directionality of the hypothesis, C, inferential test, and D, the critical value. And finally, calculate the test statistic and make a decision. Okay, so E and F on there as well. So, big problem. This is definitely indicative of how you would perform an entire Z-test. Now, I've given you all these raw scores. Right, and I'll read you this example in a second, but to preview, when you do these on the exam, although I'll show you all these raw scores, I'm going to already figure out the sample average for you and the sample standard deviation and give you those calculations already done so that you can then jump ahead to the next steps in the problem. Because I feel you've shown me this enough times now that you know how to calculate standard deviation. You don't have to prove it to me again. Okay, that being said, we'll do the whole thing here. An elementary school teacher is told he will receive a bonus if the students in his class score above the national average on an upcoming vocabulary test. Using statistical techniques he learned in a psychology statistics class as an undergraduate student. Good plug for that, right? He performs a test with a 5% significance level to see if the scores from the 19 students in his class are different from the national average on the vocabulary test. The mean of the population, the national average, for this test is 68, with a standard deviation of 13. Okay, so we know some information. Let's write it down. We're using a 5% significance level. He's asking whether or not they're different, so that's a non-directional test with 5% significance level, which means it leaves 2.5% in each tail. And actually, in our previous example, we already figured that out, right? 5% significance level with 2.5% in each tail is 1.96. So we can already write that down. The z crit or cutoff value plus minus 1.96. Okay, what else do we know? 19 students. N equals 19. See if they're different. The mean of the population is, I should make that a little bit longer, 68. And the standard deviation of the population is 13. So we know mean of population, standard deviation of the population. So we are in the world of a Z test. So if we go over here, the design of the study. Well, what is it? In this case, we have just one sample being compared to the population, so that's easy. It's a single sample study. Our research hypothesis says that in this case, the class is different, right? We're not saying what direction because the problem doesn't predict that, from the national average on this vocabulary test. Okay, non-directional, because we're not predicting what direction this will come in or who will be higher, who will be lower, simply that there will be a difference. And as I said before, we know population mean and population standard deviation, so this means we can calculate a Z test. All right, we also know the critical value, right? Because we know the cutoff value that corresponds to leaving just that 2.5% in each tail, right? So 2.5% in this tail, which means 47.5% in the middle. Same thing over here, right? And we calculated that, or I should say we looked it up in the Z table and found it to be negative 1.96, positive 1.96, critical value then plus minus 1.96. Okay. Next part of the problem, calculate the test statistic. Oh, well, crap. We got to go back to this then, because we have to calculate the test statistic using these numbers first to get the sample mean, then getting over here to finally getting standard deviation so that we can then get to standard, well, we don't actually need standard deviation in this case, but we do need the sample mean. So let's get that. So let's add all these together. All right, 68, 64, 80, 69. All right, sums up to 1,235. I'm going to do that again in my calculator just to make sure. I'm not going to make you have to watch that though. All right, it works. It's double checked. I didn't make any errors. Sample size is 19. N equals 19. All right, so again, no problem. We know how to get the calculation for the mean. 1,235 divided by 19. Hey, well, what do you know? That comes out to a nice, easy number. Rounded off, 65 with no decimals at all. Nice and easy to work with. Now, remember that the Z formula, right? And so let me actually write that down over here. The Z formula for calculating the Z statistic that we will compare to our critical value asks you to take the sample mean minus the mean of the comparison distribution, which we know to be equal to the mean of the population, which we know it was given to us, divided by standard error. So we don't actually have to figure out sample standard deviation in this case because we have a better estimate of population variability, the actual population standard deviation. Okay, so what we want to do then is take those values, right, those values that we already wrote down, right, 19, 68, 13, and 65. So let me write them down over here as well. Mean equals 68 for the population. Standard deviation is 13. Our sample mean was 65. And our sample size is 19. All right, so now we need to figure out this. So remember that standard error is equal to standard deviation divided by the square root of sample size. That's because that comparison distribution is less spread out, it's more compressed, and so we have to divide the standard deviation by the sample size in order to get the standard error of that comparison distribution, because that's not of raw scores, that's of possible values of the sample mean. Okay, so we do that first. Standard error is equal to 13, right, our standard deviation, divided by the square root of 19. All right, so it's nice and easy. Let's figure that one out. Let me get my calculator here, plug it in. We should get this to be, let's do the bottom first, we can round it properly. You'll get 4.36 down here, which 13 carries over, which means our standard error is 2.98. So then Z will be equal to our sample average, 65, minus our population average, 68, divided by the standard error that we just calculated, 2.98, would give us a value of negative 1.007 or negative 1.01. All right, we've calculated our Z statistic. Now, what was our cutoff value again? It was Z critical is equal to plus minus 1.96. Okay, so let's look at a distribution of this real quick, just so we can see what we're talking about. So if I draw this distribution here, we know that our cutoffs, so the center point is 0, our cutoffs are going to be at, shade this in, positive 1.96, oh, I forgot my x-axis, and negative 1.96. This is all the possible values of that difference between the sample mean and the population mean, right? It could take on huge differences, and sometimes they'd be positive. If the sample mean is way above the population mean, then those differences are going to be in this direction. If it's way below, then those differences are going to be in this direction. And if those differences are large enough that they're way into these tails, past these cutoffs, then we say they're really unlikely to be due to chance alone. And if they're not due to chance alone, then we reject the null hypothesis. So these cutoffs tell us 5%, 2.5 in each tail, which means a 1 in 20, 5 in 100 chance that we're wrong, right? We're willing to take that risk and say that when it occurs all the way out here, it's not likely to be due to chance because it would only happen that far out in less than 5% of the time when chance is operating, okay? Which is pretty unlikely, so it's probably not due to chance. Okay, so we had a Z statistic then of negative 1.01, so we know that it's going to be closer to 0 than that, so let's just draw it in, say it here. That falls into the realm of likely events, the highly expected events, because they're so close to the average. Therefore, we fail to reject the null. And to be more specific, we want to say something like, because this example here is about the vocabulary test compared to the national average, we would say that the students in this class do not perform differently, right? The students in this class do not perform differently from, remember from follows different, that's the appropriate idiom, differently from the national average, comma, Z sample size equals 1.01. You can include the negative if you want, but we often report the absolute value. And because this was not significant, because the chances of it being due to random error or chance alone are greater than 5%, we say P greater than 0.05. All right, and that's it. That's how you do sort of all the ways in which you would manipulate Z statistics and Z scores. All right, so hopefully that all made sense. And if not, then ask me some questions and let's get that all resolved. All right, cheers.